So, hello and welcome you all in the problem solving class of the course Principles of Signal and System. I am Vivek Kumar Srivastav, a PMRF Research Scholar of Antenna and Microwave Research Laboratory, Indian Institute of Technology, Roper, and TA of this class. So, in the previous class, we have seen numericals based on the topics discrete time signal, where we have seen how to perform sampling, quantization, and convolution theorem. Based on that, we have seen several numericals. So now in the today's class, we will try to cover a discrete time Fourier series and discrete time Fourier transform, and after that we will also cover some numericals based on the topic discrete Fourier transform. So let us start. So here is the first problem, which states that determine the discrete time Fourier series coefficient of the following periodic sequence. Okay, so periodic sequence is given to us. So corresponding to this periodic sequence, we have to determine the discrete time Fourier series. Okay, so as we all know that discrete time Fourier series can be defined as x of n is equals to summation, yeah, so summation n is equals to, basically it is defined for the time period k naught. Okay, so this is, this will be dn e raised to the power j k, just a second, j n omega naught into k. So here dn basically represents the Fourier series coefficient, sorry, discrete time Fourier series coefficient. Okay, and this dn can be evaluated by using the expression 1 over k naught summation k is equals to minus n to n x of k e raised to the power minus j n rho naught into k. Okay, so by using this expression we can evaluate the discrete time Fourier series coefficient. Okay, so now corresponding to this question, basically we have to determine the discrete time Fourier series coefficient. Okay, so here x of k basically given to us, which is h of k here. So let us proceed and solve this. So d of n can be written as 1 over k naught
Sir, can you sketch the H of K just to visualize?
Yeah, sure. So actually, it has been already given here. Okay, so this is basically drawn for a particular value of n. Okay, so like here in the problem itself, like here you can see that h of k basically a rectangular pulse. Okay, so like if suppose this is h of k, so we can plot this for various values of n, like here the h of value of h of k will be 1 when k is within the interval of minus 1 to minus n to n. Okay, so let us take an example where n is equals to 1. Okay, so it means that h of n is having a value of 1. Okay, having a value of 1 for the discrete value of minus 1, 0 and 1. Okay, and it has a periodicity of k naught. Okay, so here let us assume that k naught is equals to 10. Okay, so for other values of k, its value will be 0. So like this is 2, 3, 4, 5, 6, 7, this will be 8, and after that at 9 this will repeat itself. Okay, like here 9, 10, 11. Okay, and now again all other values will be 0. So this is how this h of n can be plotted. Okay, and it has a value of 1. Okay, now it's clear.
Uh, yes, sir.
Okay,
So k between n plus 1 into k naught minus of n plus 1. So that means you are taking care of that negative n
yeah,
also,
yeah.
negative
So
k. Yeah.
like I
Okay.
am considering this is my periodic signal. Okay, having a periodicity of 10. Okay, that is it start from -1 and it up to it at end at 8.
Okay, sir.
Okay, so now let us solve this problem. So dn we can evaluate by using this expression, which is 1 over k naught, where k varies from minus n to n, let us say. Okay, I am considering it for in general case. Okay, and it has a value of 1 between this interval, that is from minus n to n. Okay, and then e raised to the power minus j n rho naught k. And for other values of k, like k is equals to n plus 1 up to k naught. Okay, its value will be 0. Okay, so now let us solve this. So this will be 1 over k naught. So this whole term will be 0 because it is multiplied with 0. So only this term will be present here. Okay, so like we can solve this. So this will form basically a GP series. Okay, so to solve this we will use the expression of GP. Okay, which is the summation of n term, which is minus j n rho naught n, and this n will be minus n, so this will be plus. Okay, and then 1 minus e raised to the power minus j n rho naught n plus 1 over 1 minus e raised to the power minus j n rho naught. So I am taking here e raised to the power minus j and rho naught n plus 1 by 2 as a common from this expression, and from denominator I will take common as e raised to the power minus j and rho naught by 2. So this we can write it as e raised to the power j n rho naught n into e raised to the power minus j n rho naught n plus 1 by 2 over e raised to the power minus j n rho naught by 2. So the remaining terms inside the bracket will be e raised to the power j n rho naught in bracket n plus 1 by 2 minus e raised to the power minus j n rho naught in bracket n plus 1 by 2 over uh, e raised to the power j n rho naught by 2 minus e raised to the power minus j n rho naught by 2. Okay, so now we can solve it further. Okay, so like here if we can see, so let me expand this first. Yeah, so Tn will be 1 over k naught into e raised to the power j n rho naught n into e raised to the power j n rho naught. So like here if we can see, so this will be n by 2. Yeah, so I'm sorry, here this will be twice n plus 1. Okay, so this will be twice n plus 1 because we have to consider the uh, whole width. Okay, from minus 1 to 1. Okay, so like here n is 1, so the whole width will be 3. Okay, that is twice n plus 1. Okay, so that's why here it should be twice n plus 1. So now this will be e raised to the power minus j n rho naught n into e raised to the power minus j n rho naught by 2 over e raised to the power minus j n rho naught by 2. And now inside this uh, we will got this expression. Okay, so I can rewrite it as e raised to the power j n rho naught twice n plus 1 by 2 minus e raised to the power minus j n rho naught twice n plus 1 by 2 over 2j. Similarly, in denominator, we can write it as e raised to the power j n rho naught by 2 minus e raised to the power minus j n rho naught by 2. Okay, divided by 2j. Okay, so this in denominator I am writing 2j, so this will be cancelled from both numerator as well as denominator, so this will not affect the previous uh, uh, expression. Okay, so we can further solve this. So like here this numerator and denominator will cancel, whereas this two term will cancel because one term is having uh, this power as a, is in positive, whereas the second one is having a power in negative. So this will also cancel each other. So the remaining term that will come here will be sine of n rho naught n plus twice n plus 1 by 2 divided by sine of n rho naught by 2. So this is basically the discrete time Fourier series coefficient. Okay, so any doubt? Okay, so here is the solution of the previous problem. Okay, so here like as I said earlier that I've plotted this dn. Okay, for the value of n is equals to 1. So the discrete time sequence is plotted like this. Okay, it start from minus 1 and it end at 8, but it has an amplitude of 1 from minus 1 0 and 1, whereas for uh, other values of k its value will be 0, and after 8 it will repeat itself because it's a periodic sequence. So corresponding to this we have evaluated the discrete time Fourier series coefficient, which is also plotted here. Okay, so this shows that corresponding to this rectangular pulse we will got a sink like uh, distribution. Okay, so now moving ahead. So the next problem states that calculate the Fourier transform of the following function. So here we have to evaluate the Fourier transform. Okay, for unit impulse sequence, second one is gate sequence, the third one is decaying exponential sequence. So for all these three sequence we have to evaluate the Fourier transform. So let us first see that how to evaluate the Fourier transform, what is the expression corresponding to the Fourier transform. So the Fourier transform is basically uh, written as x of omega summation k is equal to minus infinite to infinite x of n e raised to the power minus j n k. Oh, sorry, j omega k. Here this will be j omega k. Okay, so by using this expression we can evaluate basically the uh, discrete time Fourier transform of any non-periodic signal. Okay, so like here if you can see that these three are basically non-periodic signals. Okay, like in the previous problem we have seen that how to evaluate the Fourier series coefficient corresponding to a periodic sequence, whereas the discrete time Fourier transform is evaluated only for non-periodic sequence. Okay, here like here we can see that it is evaluated for non-periodic sequences, but later we will also see that Fourier transform can also be used for evaluating uh, uh, continuous time sorry discrete time Fourier sorry discrete time sequence, okay, which is basically periodic in nature. Okay, so like let me explain first. So Fourier discrete time Fourier series basically used for periodic sequence, whereas discrete time Fourier transform is used for both periodic as well as non-periodic sequences. Okay, so here like in this problem the sequences that is given to us is non-periodic in nature. So for that we will use this expression, whereas to obtain the discrete time Fourier transform corresponding to a periodic sequence we will use some another expression that we will see in the upcoming slides. Okay, so let us try to solve this uh, problem by using this expression of discrete time Fourier transform. So let us take the first case where we will use the sequence as unit impulse sequence. Okay, that is x1k is equals to delta of k. So what we have to do, we have to just replace xn with delta of k is minus infinite to infinite delta of k into e raised to the power minus j rho k. So like here if we can see that delta of k is only defined for a value of k is equals to 0. So let me plot it here. So like delta of k is defined for value of k is equals to 0. So that's why the the summation can be evaluated as summation k is equals to minus infinite to infinite delta of k or this will be e raised to the power minus j rho k at k is equals to 0. So that once you evaluate, so here like we can ignore the summation because this summation is satisfying only for k is equals to 0. So you can directly put k is equals to 0 here and you will get the discrete time Fourier transform as 1 for unit impulse sequence. Okay, whereas for the gated sequence that is x2k, which is a rect signal, okay, rectangular signal, which is defined within the interval of minus n to n and it has a value of 1. So let me plot. So let us say that this is a, yeah, so this is basically x2n, okay, which is defined x2k, let us say, okay, which is defined from minus n to n and have 0 value for other values of k. Okay, so this is basically the plot of x2k. So uh, the Fourier transform corresponding to this x2k is evaluated as summation k is equal to minus n to n. Its value is having a value of 1 in between this interval into e raised to the power minus j rho k. Okay, so this we can solve like we have like we already solved the previous problem. Okay, so I will solve this once for you. Okay, so this will be e raised to the power j rho n 1 minus e raised to the power j rho twice n plus 1 over 1 minus e raised to the power j rho. So this we can further solve into, so like from numerator I will take e raised to the power. Okay, so here this will be minus. Okay, so I will take from numerator as a common as a factor of e raised to the power minus j rho twice n plus 1 by 2. So in bracket we will get e raised to the power j rho twice n plus 1 by 2 minus e raised to the power minus j rho twice n plus 1 by 2 divided by e raised to the power minus j rho by 2 e raised to the power j rho by 2 minus e raised to the power minus j rho by 2. Okay, so once you solve this terms will cancel each other. So we will get the Fourier transform like sine of 2n plus 1 by 2 rho divided by sine of rho by 2. Okay, so this is basically the discrete time Fourier transform corresponding to the gate sequence that is given in the part 2 of this question. Okay, so now moving to the next part, that is the decaying exponential signal, that is x3. Okay, so x3 is basically defined as p raised to the power k uk. Okay, okay, so where p is basically less than 1. Okay, so to determine the Fourier transform we will use the same expression, that is k varies from minus infinite to infinite x of k e raised to the power minus j rho k. Okay, so let us put the value of x of k x3k here in this expression. So we will get summation k is equals to minus infinite to infinite p raised to the power k u of k into e raised to the power minus j rho k. So as this
Sir,
yes,
sir, just one confusion.
yes,
Normally, as a convention, we use K for frequency coefficient, right? In DTFT, we use N for time domain representation, right?
yes, you can use any
In,
notation.
yeah, generally in convention, when you say N, small n, we use it for time domain, and
Mm-hmm.
small k for frequency. In DFT, we use frequency coefficient. So here omega is an analog frequency. Sorry, yeah, it is.
Continuous frequency.
Yeah, it is continuous, right?
Yes,
Continuous.
yes.
Okay, okay, okay. So that is the reason. Oh, if it is continuous, yeah, maybe at some point, I always get confused. Somewhere we use integral, somewhere we use a sigma in DTFS, DTFT, DFT. Maybe in 5 minutes somewhere you can write down all at one place,
Mm-hmm.
to avoid that confusion. Maybe later. Okay, go ahead,
Okay,
sir.
so yeah, so we can solve it like here like we can see that u of k is present. So u of k, as we know that unit step function is defined from k is equals to 0 up to infinite. Okay, so like here we can write summation k is equals to 0 up to infinite p of k into e raised to the power minus j rho k. Okay, so summation k is equals to 0 to infinite p into e raised to the power minus j rho raised to the power k. So like this is basically the gp series. Okay, summation of uh, nth order of gp series. Okay, or sorry, infinite number of gp series. So the summation of this kind of gp series is written as 1 over 1 minus r, which is p e raised to the power minus j rho. Okay, so this is basically the Fourier transform, that is discrete time Fourier transform corresponding to decaying exponential function. Okay, so here is the solution of uh, these three signals. Okay, Fourier transform uh, evaluation of these three signals that we have seen. Okay, and the plot corresponding to these signals is also given here. So like in in the second part of the problem we have seen that that it is a rectangular signal, and corresponding to this we have got this kind of Fourier transform. So once we plot this, we will get this kind of signal. Okay, that is distribution basically. Okay, which shows that uh, in discrete time Fourier transform, the Fourier transform is basically continuous in time. Sorry, continuous in frequency. So here this will be continuous in frequency. Similarly, in the third part we have seen that this is basically a decreasing exponential function. Okay, so corresponding to this we have got this expression, that is the discrete time Fourier transform. So here is the plot of the real part of discrete time Fourier transform, and the sorry, magnitude of discrete time Fourier transform, and the phase of discrete time Fourier transform, which also shows that it is continuous in frequency. Okay, so after performing discrete time Fourier transform, we will get uh, a function that is continuous in frequency basically. Okay, so now
So sir, when you say continuous, omega,
yes,
omega is 2 pi by n, right?
that you have to take in discrete Fourier transform.
Oh, here, how do you define omega? Angular frequency is
See,
2 pi
like
by
for
t.
discrete time Fourier transform, for all kind of signal you will get continuous in frequency having a periodicity of 2 pi.
Yes. So here the definition is 2 pi by t,
2 pi by t.
capital T period.
2 pi itself is period.
Oh, 2 pi,
So like
2
here you
pi.
can see, like if you are confusing, so like here I have already plot the discrete time Fourier transform. So this corresponds to one fundamental period of x to omega. Okay,
Yes.
so this is basically the period, okay, which is having a value of 2 pi. Similarly, for this decaying exponential signal, you can see that the period is having a value of 2 pi here also.
Okay. 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 That means for all Fourier series,
Yes,
whether it's discrete or continuous, the period is 2 pi anyway, right?
yes,
Sorry, the
Fourier
yeah, the
transform.
yeah, Fourier transform period is 2 pi.
Yes.
Right. Yes. Okay.
Okay, so
Okay.
moving ahead.
Okay.
So here we have to calculate the discrete time sequence for the following yeah, so here basically a discrete time sequence is given. uh, we have to basically calculate here the discrete time sequence corresponding to this discrete time Fourier transform. Okay, so here discrete time Fourier transform is given to us. Corresponding to this discrete time Fourier transform, we have to evaluate basically this sequence. Okay, so basically here we have to use the synthesis expression of discrete time Fourier transform, which can be written as, yeah, so like x2k x1k is basically written as 1 over 2 pi integral x1 omega into e raised to the power j k omega dot d omega. Okay, so as I said earlier that uh, the discrete time Fourier transform is defined for a period of 2 pi. So like, hello, yeah, are you saying
Yes, sir.
something?
Yes, sir.
Okay,
Sorry, sir. Go ahead. Go ahead.
okay, so like as I said earlier that the discrete time Fourier transform is having a period of 2 pi. So to obtain the discrete time sequence, we will use this expression and integrate this x1 omega for a period of 2 pi. Okay, so as you already know that x1 omega is given to us, that is 2 pi summation m is equals to minus infinite to infinite delta of omega minus 2 m pi. Okay, so that you have to put here, okay, in place of x1 omega. So that I put it here. Okay, so once you put, you can see that this 2 pi and 2 pi will cancel each other. Okay, so the remaining term here will be integral minus pi to pi here, sorry, this will be from minus pi to pi summation m from minus infinite to infinite delta of omega minus 2 m pi into e raised to the power j k rho dot d rho. Okay, so now we will use this property, that is delta of rho minus theta into f of rho is equals to delta of rho minus theta into f of theta. So we will use this property. So when we will use this property, we will put this rho in the expression of e raised to the power j k rho, as rho will be replaced by 2 pi m here. Okay, so like here I've used this property. So in the expression I put e raised to the power j k into 2 m pi. Okay, so as we know that e raised to the power j k 2 m pi. Okay, so this is basically a complex exponential signal. Okay, and having a value of 1 for every integral value of 2 m pi. Okay, so that's why I put the value of e raised to the power j k 2 m pi as 1 here in the expression. Okay, so once I put this, so the remaining term will be integral minus pi to pi summation m varies from minus infinite to infinite delta of omega minus 2 m pi into d omega. Okay, so now if you will plot this function, okay, so you can see that delta of omega minus 2 m pi is plotted as, here this is having a value of 1 at rho is equals to 0, that is omega is equals to 0. Then you will get a value of 1 again at 2 pi and minus 2 pi, then 4 pi you will get value of 1, and minus 4 pi you will get value of 1, and so on. But here if you see that we are integrating this expression from minus pi to pi, that is from here to here. Okay, so we are integrating this from here to here, and here we can see that this delta of rho minus 2 m pi is defined only for uh, omega is equals to 0 here. Okay, so once you evaluate this expression, you will get x1 of k is equals to 1, because this is defined only for the value of omega is equals to 0. Okay, so you will take integral from minus pi to pi, but for other value of omega this will be 0. This is only defined for omega is equals to 0 and having a value of 1, so that's why x1 of k will be equals to 1 here. So any doubt? So now moving ahead. Yeah, so this in this problem we have to determine if the discrete time Fourier transform exists for causal exponential function. Okay, so basically we have to check whether discrete time Fourier transform will exist for this causal exponential function or not. Okay, so from the
Sir,
yes,
sir, generally causal function means if u of k is there, then we can say it is a causal, right?
yes,
U of k is right hand side.
yes,
Uh,
because u of k is defined for all positive values of k.
yes, so
Okay,
it is causal.
yeah.
Okay, 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 sir.
So yeah, yeah. So like here we have to check whether discrete time Fourier transform will exist for this causal exponential function or not. Okay, so to exist the this causal to exist any discrete time Fourier transform, basically the x of omega should be finite, then only discrete time Fourier transform will exist. Okay, and if that is the magnitude of x of omega will be finite, so if this condition will satisfy, then only we can say that the discrete time Fourier transform will exist, and if this condition will not satisfy, then the discrete time Fourier transform will not exist. Okay, so alternately we can also say that, yeah, alternately we can say that as we know that x of omega can be written as k varies from minus infinite to infinite x of k into e raised to the power minus j omega k. Okay, so let us put the value of x of omega here. Okay, so this will be summation k varies from minus infinite to infinite x of k into e raised to the power minus j rho k. Okay, this should be finite. This should be finite here. Okay, so we can also write it as this should be finite. Okay, so as we already know that the magnitude of complex exponential function will be equal to 1. Okay, always the magnitude will be 1 here, so the remaining part will be summation of k varies from minus infinite to infinite mod of x of k will be finite. Okay, so alternately we can say that if this condition will satisfy, then only we can say that the discrete time Fourier transform will exist. Okay, so here as in the question itself it is given that x1 of k, that the sequence is given to us, so we will use this expression to check whether the discrete time Fourier transform will exist or not. So let us try. So where k varies from minus infinite to infinite p raised to the power k into u of k. Okay, so we can uh, so this k will start from 0 to infinite because this is a causal exponential function. Okay, so that's why this start from 0 to infinite, and argument will be p raised to the power k. So this is basically a gp series. Okay, and the sum of this infinite term gp series will be 1 over 1 minus p. Okay, it means that this uh, this summation or this condition will satisfy only when the value of p lie between 0 to 1. Okay, and at p is equal to 1, this value will go to infinite. Okay, so it means that for p is equal to 1, okay, this discrete time Fourier transform will not exist, whereas for the value of p lie between 0 to 1, the we can get basically the discrete time Fourier transform, or we can say that discrete time Fourier transform will exist. Okay, so any doubt?
Okay, sir. Okay.
Okay, so now moving ahead. So the next problem is calculate the dtft of x1k that is equal to k within where k varies from 0 to 3 and with a fundamental period of k is equal to 4. Okay, so like here as I said in the previous problem, so here the discrete time Fourier transform is defined for both periodic as well as non-periodic signal. So to determine the discrete time Fourier transform for non-periodic signal, we have seen in the previous problem that uh, which expression has to use to evaluate the discrete time Fourier transform for non-periodic sequence. Okay, whereas to determine the discrete time Fourier transform uh, corresponding to the periodic signal, uh, we will first we will first have to see that how to basically uh, determine or say how to basically show the discrete time Fourier transform corresponding to a periodic sequence. Okay, so let us say that x of k here is a periodic sequence. Okay, so corresponding to this x of k, the discrete time Fourier transform is defined as x of omega is equal to 2 pi summation n varies from minus infinite to infinite d of n delta of omega minus 2 n pi over k naught. Okay, so by using this expression we can evaluate the discrete time Fourier transform corresponding to a periodic sequence. Okay, so like here you can see that here discrete time Fourier transform we have to evaluate for value of n varies from minus infinite to infinite. It means that here discrete time Fourier series coefficient, that is dn, here we have to evaluate for n is equal to 0 plus minus 1 plus minus 2 plus minus 3 plus minus 4 and so on. Okay, so for all values of n you have to first determine the value of dn. Okay, and then you have to put the value of dn in this expression. Okay, so as to obtain the discrete time Fourier transform. Okay, so but here we have to see an important property of the discrete time Fourier transform for a periodic sequence, which states that if suppose you have a discrete time Fourier transform, discrete time sequence which is defined for a specific period, let us say k, capital K, okay, or say k naught. Okay, so or you can say that this x of k is basically defined only for some interval that is varying from minus n to n. Okay, so between this interval you have to evaluate the value of dn, that is the discrete time Fourier series coefficient. Okay, so once you evaluate the discrete time Fourier series coefficient, so now you don't have to evaluate the remaining discrete time Fourier series coefficient. You have to just use this relation, that is dn plus k naught is equals to dn. Okay, so by using this expression, you can evaluate the remaining value of dn. Okay, so it means that we have to only evaluate the value of dn within this interval only. Okay, and the remaining value of dn can be evaluated by using this expression. Okay, so let us first determine the value of dn within the interval, okay, which is given to us, that is from 0 to 3. Okay, it means that we have to determine the value of d naught, d1, d2 and d3. Okay, and the remaining value of d d can be evaluated as, so like here, if you want to evaluate the value of d4, okay, so what you have to do, d of, let us say here k is 4. Okay, so what you have to do, you have to take 0 plus 4 is equals to d0. It means that d of 4 will be equals to d0. Similarly, d of 5, if you want to evaluate, you have to, this will this will be equals to d of 1. Okay, so similarly you can evaluate the other value of different discrete time Fourier series coefficient. So now the question comes that how to evaluate the value of discrete time Fourier series coefficient within this interval, okay, which is specified to us. Okay, so for that we will use this expression, that is dn is equals to 1 over k naught. It is summation uh, k varies within the interval of k naught, okay, x of k e raised to the power minus j n rho naught k. Okay, so by using this expression we will evaluate the value of discrete time Fourier series coefficient. Okay, so let us first determine the value of omega naught. Okay, so like here we can also write this, let me remove this first of all. Yeah, so we can also write it as 2 pi summation n varies from minus infinite to infinite dn delta of omega minus n omega naught. Okay, so first of all we have to evaluate that what will be the value of omega naught. Okay, so like here k naught is given to us in the problem, okay, which is 4. So we will put the value of k naught 4 here. Okay, and after solving we will get that the value of omega naught will be equals to pi by 2. Okay, so value of omega naught will be equals to pi by 2. So let us now proceed and evaluate the value of dn. Okay, so for evaluating dn we will use this expression. So dn is equals to 1 by k naught, which is 4 here, summation k varies from 0 to 3 k e raised to the power minus j n k into pi by 2. Okay, because we have to see here, this basically correspond to the uh, frequency shifting. Okay, so basically we will use the frequency shifting property. So if you basically shift in frequency, so in the uh, in the time you will get a multiplication with a factor of e raised to the, exponential factor basically. Okay, so that's why here we are multiplying with the exponential factor. Okay, that is e raised to the power minus j n pi k by 2. Okay, so now we will put the value of k here, which is 0, 1, 2 and 3. So after putting the value of k here, you will get the value of dn as 1 by 4 e raised to the power minus j n pi by 2 plus 2 e raised to the power minus j and pi plus 3 e raised to the power minus j 3 and pi by 2. Okay, so this is basically the expression of dn. So now uh, to evaluate the value of uh, discrete time Fourier series coefficient for a particular value of n, we will put the value of n as 0, 1, 2 and 3. So once you put the value of this value of n, you will get the value of discrete time Fourier series coefficient as d0, d1, d2 and d3. So this mathematical part I am leaving to you. Okay, so you can evaluate it later. Okay, so once you evaluate, so you can put the value of d1, d2, d3 here in this expression so as to get the discrete time Fourier series discrete time Fourier transform corresponding to this periodic sequence which is given in the problem. Okay, so any doubt in this problem?
No problem, sir.
Okay.
See, sometimes I always get confused. DT, this is a discrete time Fourier series periodic
Yes.
versus DFT. The formulas of DFT
Yes. Yes.
and discrete time FS of
See,
periodic
DFT is
look
different.
similar.
DFT is different.
Yes.
That we will see in the later in this class. Okay, or maybe in the next class. Okay, so
Okay.
DFT is different thing, but discrete time Fourier series or discrete time Fourier transform is different thing.
Yes. 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 I understand. Sometimes the formulas,
Yeah, it is little bit
similar.
difficult. I can understand. Yes.
Yeah, yeah. So I always get confused that formulas. I know the difference conceptually, but when writing formulas instead of this, in DFT we don't use infinity, right? We use only n,
Mm-hmm.
0 to n minus 1.
Yes.
Okay, and here infinity, yeah. Okay. Anyway, sir. Okay, go ahead.
Okay. So yeah, no, moving to the next problem. So here, basically using the time shifting property, we have to basically calculate the discrete time Fourier transform of the following sequence. Okay, so basically here x of k is defined as a sequence of basically linear combination of two different sequence which is defined for two different periods. Okay, so like here the first sequence is the rectangular pulse like you can see here, which is defined within the interval of 3 to 9, whereas the second sequence is the exponential decaying signal. Okay, and it start from 12 and end up to infinite. Okay, so like here, like if we can draw this signal, so this will start from 3 up to 9. This is having a value of 0.75. Okay, so this is having a value of 0.75, whereas from 12, okay, this is basically a decaying exponential signal. Okay, so here we can say that x of k is basically a linear combination of rectangular signal and decaying exponential. Okay, so like we already know from our previous problem that let us say x2k is equals to 0.75. Okay, which is defined for an interval of 3 to 9. Okay, so from previous problem we have seen that if this is my rectangular signal which is defined from minus n to n, okay, so corresponding to this discrete time sequence, we will get the Fourier transform as sine of twice n plus 1 by 2 omega over sine of omega by 2. So this is basically the discrete time Fourier series coefficient, discrete time Fourier transform corresponding to this rectangular sequence. Similarly, for this kind of exponentially decaying signal, okay, we have seen that if this is the peak value of p, okay, so corresponding to this we already seen that the x of omega is defined as 1 over 1 minus p e raised to the power minus j omega. Okay, so now we will use the shifting property of discrete time Fourier transform, okay, so as to get this kind of signal, okay, that is given to us. So uh, x of k is basically defined as 0.75 times x2k minus, basically here if you can see, so like here this will be 0, okay, so the midpoint will be 0, that is it start from minus n goes up to n and having a mid value of omega as 0. But here, like here in this signal, the mid value lie at uh, uh, omega, or say n is k is equals to 6, okay, it means that this is the shifted version of x of n, okay, so that's why I will write this as 0.75 x2 k minus 6, okay, whereas the second signal, like here you can see that it is shifted by a uh, time of 12, okay, so that's why
Sir, see, in time domain, we are shifting left, right. When we are shifting left,
yes,
it should be plus, no? Plus 6, no?
but here I am shifting in the right side, no, this is my original signal, like here in the previous
Yes,
problem
yes, yes.
we have seen.
Okay, okay.
Just a
Yeah, yeah.
moment.
Oh, okay,
Yeah,
okay. So the original previous problem, you are shifting right.
yes,
So
yes,
it is minus.
yes,
Okay. Yes.
okay.
Yeah, yeah.
So similarly, for
Okay.
this kind of signal x3k, okay, which is defined as p raised to the power k u of k, okay, so corresponding to this signal, okay, we will get the transform of x3 omega is equals to 1 over 1 minus p e raised to the power minus j omega, okay, so we can write this as 0.5 raised to the power k minus 12 into x3 k minus 12, because it is shifted to the right side, okay, for a time of 12, okay, so like now we can use the time shifting property. So x of omega is basically defined as 0.75 sine of 2n plus 1 rho by 2 over sine of rho by 2 into e raised to the power minus j 6, okay, plus here this should be omega, and yeah, for this will be 0.5 over 1 minus p e raised to the power minus j rho into e raised to the power minus j12 rho. So this is basically the discrete time Fourier transform corresponding to this signal. Okay, so any doubt in this problem? Okay, so here this P should be 0.5. Any doubt?
So, sir, that shifting only, can you explain? I always confuse the left shift. See, the original function given to us is already a shifted function at 6, right? Centered at 6.
No, see,
No.
this is my original signal. Okay,
Yes.
okay, this is
Yes.
my original signal. From this original signal, I am deriving this. Okay,
Oh,
so
from original signal, you are deriving the given signal.
yes, yes, yes. Okay, so for that,
Okay.
what I will do, I will shift this original signal by a time of 6. Okay, towards the right
Yes.
side.
Right.
Okay, similarly for this decaying exponential signal, what I will do, I will shift this original signal towards
By
the
12.
right side.
Okay. Okay.
Okay,
Okay. 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 Okay, sir. I got it.
okay. So now moving ahead, yeah. So here the problem states that using the frequency shifting property, calculate the discrete time Fourier transform of x of k, which is given as cos of rho naught k into cos of rho 1 k. Okay, and here rho naught plus rho 1 will be less than pi. So as we know, first of all, that twice cos of omega naught k into cos of omega 1 k, this can be written as cos of rho naught plus rho 1 k plus cos of rho naught minus rho 1 k. Okay, so this I've got from the mathematical identity. Okay, so now as we know, or we can write it as cos of rho naught k into cos of rho 1 k as 1 by 2 cos of rho naught plus rho 1 into k plus 1 by 2 cos of rho naught minus rho 1 into k. So now as we know from this for discrete time Fourier transform of cos function, which is written as pi delta of omega minus, or say omega plus omega naught minus 2 m pi plus delta of omega minus omega naught minus 2 m pi. Okay, so this basically you can evaluate by using discrete time Fourier transform. Okay, so you will get this expression. So I will use this basically formula so as to evaluate the discrete time Fourier transform of this expression. Okay, so like here the final expression that come as 1 by 2 cos of rho naught plus rho 1 k plus 1 by 2 cos of rho naught minus rho 1 k. Okay, so I will use this identity so as to evaluate the final Fourier discrete time Fourier transform. So let us proceed. Rho naught k into cos of rho 1 k. So this we can write it as pi by 2. So this I will take common. Okay, so further we can write it as delta rho plus rho naught plus rho 1. This will be minus 2 m pi plus delta rho minus rho naught minus rho 1 minus 2 m pi plus delta rho plus rho naught minus rho 1 minus 2 m pi delta rho minus rho naught plus rho 1 minus 2 m pi. So this is basically the discrete time Fourier transform corresponding to this signal that is given to us, that is cos rho naught k into cos rho 1 k. So any doubt? So now moving ahead. Yeah, any doubt?
No, 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 sir.
Okay.
Just I'm curious. In the formula, 2m pi is there.
Yeah.
Is it m is what?
Sorry.
M. Yeah, in the formula for cos omega naught k
Hmm.
dtft,
Hmm.
the m is the m is oh, it is
It
okay.
is
Okay, it
periodic
is
in nature.
series periodic.
Yeah.
Okay, 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 sir. I got it.
So now moving ahead. So the next problem is based on the discrete time Fourier transform of unit step and the time shifting property, calculate the discrete time Fourier transform of x of k, which is equals to uh, delta function. Okay, so here basically uh, based on the discrete time Fourier transform of unit step and the time shifting property, we have to evaluate the discrete time Fourier transform of delta of k. Okay, so as we know that the discrete time Fourier transform corresponding to unit step function is defined as pi summation m varies from minus infinite to infinite delta of omega minus 2 m pi plus 1 over 1 minus e raised to the power minus j omega. Okay, so that you can get from any standard book, or you can also evaluate by yourself. Okay, so I will use this property. Okay, I will use this expression of u of k so as to determine the uh, discrete time Fourier transform of delta of k. So for that we will use the time differentiating property. Okay, so time differentiating property states that u of k minus u of k minus 1 will be equal to, or say like for an in general signal x of k, let us suppose. Okay, so time differentiating property states that x of k minus x of k minus 1, the Fourier transform corresponding to this time differentiating will be 1 minus e raised to the power minus j rho into x of omega. Okay, so by using this we can evaluate the uh, Fourier transform of time differentiating property, time differentiating signal. Okay, so like here I will use this property. So u of k minus u of k minus 1, so corresponding to this time differentiating, the discrete time Fourier transform is defined as 1 minus e raised to the power minus j rho into the Fourier transform of u of k, which is given here. Okay, so now what we will do, we will multiply this factor inside this bracket. Okay, so like first of all we will multiply this factor by this. Okay, so we will get a value of 1. Okay, whereas once we multiply this with the first factor we will get this expression. Okay, so now we will use the same property, that is delta of rho minus theta into x of rho is equals to delta of rho minus theta into x of theta. Okay, so we will use this property. So we will replace here in the expression of 1 minus e raised to the power minus j omega, where omega will be equals to 2 m pi. So once we put the value of omega as 2 m pi, okay, so e raised to the power minus j 2 m pi. Okay, so the value of this at integral multiple of 2 m pi will be equals to 1. Okay, so that's why this whole term will be equals to 0, because you have to subtract this 1 minus 1, so the whole term will be equals to 0. So that's why the discrete time Fourier transform will reduce to this, that is delta of k will be having a discrete time Fourier transform of 1. Okay, so any doubt?
Okay, sir. Okay.
Yeah. So yeah, next problem is based on the discrete time Fourier transform of exponential decaying function and frequency differentiation property, calculate the discrete time Fourier transform of x of k, which is equal to k plus 1 into p raised to the power k into uk. Okay, so yeah, so as we know that the differentiation property states that in frequency states that minus jk x of k is having a discrete time Fourier transform of d by d omega x of omega. Okay, so this corresponds to the discrete time Fourier transform of uh, minus jk x of k. Okay, so we will use this property so as to evaluate the discrete time Fourier transform of this function. So as we know from our previous problem that the discrete time Fourier transform of this exponentially decaying function is p raised to the power k uk is defined as 1 over 1 minus p into e raised to the power minus j omega. Okay, so now if you can see here, this function can be further written as k into p raised to the power k uk plus p raised to the power k into uk. Okay, so corresponding to this function we have already evaluated that what will be the discrete time Fourier transform, but for evaluating the discrete time Fourier transform for this first function we will use the frequency differentiation property, which states that if suppose x of k is given to you, okay, which is having a discrete time Fourier transform defined as x of omega. So if you differentiate this x of omega with respect to omega, okay, so the corresponding time domain signal will be multiplied by a factor of minus jk. Okay, so we will use this property. So like here x of k that is given in the problem is p raised to the power k into uk, and corresponding to this function we already know that what will be the discrete time Fourier transform. Okay, so minus jk into p raised to the power k uk will having the discrete time Fourier transform of d by d omega into 1 over 1 minus p into e raised to the power minus j omega. So you have to differentiate this function with respect to omega. So once you differentiate you will get this expression. Okay, so now we can basically uh, cut this value of minus j from both the side. So you will get k into p raised to the power k uk is having a discrete time Fourier transform of p into e raised to the power minus j omega over 1 minus p into e raised to the power minus j omega square. Okay, so now you have to just take summation of these because the overall signal is the summation of these two individual signals. Okay, so the corresponding discrete time Fourier transform will always be uh, summation of these two Fourier transform from the linearity property. Okay, so once uh, you take summation you will get the discrete time Fourier transform of the function x of k. Okay, any doubt? So
Okay, sir.
yeah, so now moving ahead. So uh, this problem states that the exponential decaying sequence x of k is equal to a of k into u of k, which is where a is having a value within the range of 0 to 1 is applied at the input of linear time invariant discrete time system with a impulse response h of k, okay, where h of k is also defined is equals to b of k into u of k. Okay, so using the discrete time Fourier transform approach, calculate the output of the system. Okay, so this kind of problem we have already solved by using time domain method. Okay, where we have seen that if x of uh, k is given to us, h of k, that the impulse response of the system is given to us. So if we want to evaluate the y of k, so we have used the convolution sum method, okay, so as to evaluate the y of k that we have seen in the previous class. So now in the today class we will solve the same problem by using convolution approach. So convolution approach states that in the time domain, if you want to evaluate output or say response of the system, so this response is basically defined as convolution of input applied to the system and the impulse response of the system. But if uh, if you uh, if you analyze the system in the frequency response in the frequency, so y of omega is basically a multiplication of x of omega into h of omega. Okay, so this is basically a uh, uh, property basically of discrete time Fourier transform. Okay, so we will use this property. Okay, so first of all, instead of analyzing this signal in the time domain, we will first transform this signal in the frequency domain, and then we will use this property so as to analyze this system. So x of k basically, which is given to us as a raised to the power k into uk, so corresponding to this signal you will get the discrete time Fourier transform as 1 over 1 minus a into e raised to the power minus j omega, so that we have seen from our previous questions. Similarly, h of k is defined as Fourier transform of this h of k is defined as 1 over 1 minus b e raised to the power minus j omega. Okay, so now y of omega is basically defined as multiplication of uh, x of omega into h of omega. So x of omega we have already evaluated, h of omega we have already evaluated, so y of omega is basically a multiplication of these two signals. Okay, so from here we can further solve this y of omega, but it's better to take two cases. The first case is when a is equals to b. So in this case the transfer function will be defined it like 1 over 1 minus a into e raised to the power minus j omega raised to the power 2. Whereas when a is not equals to b, this expression will remain the same. Okay, so now I am going to show you that how to evaluate the uh, system response, okay, by using uh, partial fraction method. Okay, so like I'm using first case where a is not equals to b. Okay, it means I will use this transfer function, and corresponding to this transfer function I will evaluate the uh, this coefficient a and b, okay, by using partial fraction method. Okay, that uh, and how to evaluate this value of a and b, that we have already seen from the previous class. Okay, so I leave this exercise for you so as to evaluate a and the value of b by yourself. Okay, so once you evaluate, the value of a will come as a over a minus b, and the value of b will be equals to minus b over a minus b. So now you will put the value of a and b here in this expression of y of omega, and take the uh, inverse basically uh, Fourier transform. Okay, so after taking inverse Fourier transform you will get this expression. Okay, because we have already seen this, that corresponding to this expression 1 over 1 minus sorry a into e raised to the power minus j omega, the the signal time in time domain, this is defined as a raised to the power n u of n. Okay, so like here a is already present, so this a and a raised to the power n will multiply, and the overall factor will come here as a raised to the power k plus 1. Similarly here, due to the presence of one b factor in the in this coefficient, this will become as b raised to the power k plus 1. Okay, so that is how you can evaluate the response. Similarly you can solve the response where a is equals to b. Okay, so I am leaving this exercise for you, you can evaluate this by yourself. So the final value, once you evaluate, so the y of k will come as k plus 1 into a raised to the power k u of k plus 1. Okay, so the final value of y of k when a is equals to b is defined it like this, whereas when a will not be equals to b, the final value of y of k will be defined it by this expression. Okay, so now moving to the next problem. So here we have to calculate the 4-point discrete Fourier transform of a periodic sequence x of k of length n is equals to 4, which is defined as follows. Okay, so x of k is given to us. Okay, corresponding to this x of k we have to evaluate the discrete Fourier transform. Okay, so to evaluate the discrete Fourier transform, we will use this expression, that is x of r is equals to summation k is equals to 0 to 3 x of k into e raised to the power minus j into 2 pi k r by 4. Okay, so basically x of r in general is defined as, okay, so like here you can see from the previous problem, what this the only difference here in this expression is that we discretize the value of omega. Okay, by a factor of 2 pi r over m. Okay, so this is the only difference here. It means that here in the discrete Fourier transform, the the Fourier transform is basically discretized in nature in comparison to the discrete time Fourier transform, where the omega, that is the frequency, is continuous in nature. Okay, so this is the only difference here in the discrete Fourier transform. Okay, so by using this expression we will evaluate the discrete Fourier transform x of r. Okay, so now first of all what we will do, we will put the value of k as 0, 1, 2 and 3. So once you put the value of k, you will get this expression x of r. Okay, so now to evaluate the discrete Fourier transform at for uh, yeah, so now for evaluating the discrete Fourier transform for various value of r, we will put the value of r as 0, 1, 2 and 3, because normally what we will do in the discrete Fourier transform, whatever the discretization period we will take at the input side, the same discretization period we will take at the output side. Okay, so that's why I analyze this for r is equals to 0, 1, 2 and 3. So here in this expression I will put the value of r as 0. So I will solve this and I will get the value of x of 0 as 5. Similarly I will put the value of r as 1, 2 and 3, so as to get the other coefficients. Okay, so once I know this coefficient, okay, so uh, basically we have to put this in the expression so as to get the discrete Fourier transform. So now moving ahead, so in this problem we have to basically evaluate the inverse discrete Fourier transform. Okay, so x of r is basically given to us. Okay, and here we have to evaluate the uh, sequence, basically discrete time sequence. Okay, that is x of k, that we have to evaluate. Okay, so x of r is given to us. So on the basis of this x of r we have to evaluate the different values of x of k. Okay, so first of all, to evaluate this x of k, we will use synthesis equation of discrete Fourier transform, which is defined as x of k is equals to 1 over k naught summation r is equals to 0 to, yeah, n minus 1 x of r e raised to the power j 2 pi k r over 4, or say k naught. Okay, so by using this expression we will evaluate the inverse discrete Fourier transform. Okay, so I will put the value of k as 4 because here 4 steps are there. Okay, and this r will varies from 0 to 3. Okay, and yeah, I will first evaluate the x of k for different values of r, such as r is equal to 0, 1, 2 and 3. So after putting the value of r I will get this expression. Okay, so now to get the coefficients of discrete time signal, that is x of 0, x of 1, x of 2 and x of 3. Okay, I will put the value of k in this expression as 0, 1, 2 and 3, and I will get this, uh, yeah, I will get this coefficients. Okay, so that's how we can evaluate, or say we can use this expression of analyzing equation and synthesis equation of discrete Fourier transform to evaluate the different coefficients. Okay, so that's all for the today's class. Thank you.